So in our notes today, what we're going to do is we're going to copy down some information on the Pythagorean Theorem. Your goals are to understand what the Pythagorean Theorem is and how it can be used. And the nice thing is we've actually been working on the Pythagorean Theorem. This is not something we're learning from scratch. This is something we're actually just taking information we've been doing in class and summarizing. And in fact, what it's been is our community center project is actually the Pythagorean Theorem. So if you think about it, what we've been doing is we've been given a proposed right triangle, which represents our playground courtyard. We were supposed to add on square buildings along each side and then find all the measurements. Well, really what it gets down to is that we've been using these squares to actually find the relationship between the three sides of the triangle. That the squares were just tools to get us to the answer, but what we were looking for is some kind of relationship that if I knew two sides, the measurements of the triangle, that I could use the squares to find the third side. And in class we came up with a lot of conclusions, so what we're going to do is we're going to talk about those conclusions. So let's take a look, let's redraw this triangle, and let's actually put in some measurements. This in fact might have been one of the proposed blueprints that one of your groups worked on. So 9 meters by 12 meters. So if you recall what we talked about in class, we discussed how you would first take the buildings and add them on. So here we get a 9 by 9 building, here a 12 by 12 building. We wanted our buildings to go corner to corner. And so that information we could record down. Side length of the small building, 9 meters. Side length of the medium building, 12 meters. And it's this next part where we started to have some group discussions. That I could add on the next building, but I couldn't record down the information as far as the side length because it didn't line up with our graph paper. We couldn't just count squares like we could on the others. And so how do I find the side length of the large building? Well, eventually what we discussed was that we skipped over that temporarily, that we would come back to that later, that at the moment we don't have enough information to find the side length of the large building. So what we then went next to is the three columns in the end, the areas. Now area was pretty easy for this one. If it was 9 by 9, I could see the graph paper squares, or I could just do the math. 9 times 9 is 81 square meters. I could do the exact same thing for the medium building. 12 by 12, 12 times 12 is 144, and so I could find that area. And then finally the area of the large building. Now this was a little trickier, but we did some work on the previous video to figure this out. We basically chopped up our square and dissected it, rearranged the pieces, taped it all back together, and then we were able to count squares. Now in this case, since I don't have graph paper on the computer, we're just going to tell you that that would have counted out to be 225 square meters. Now, one of the key ideas that you guys came up with, which we discussed afterwards, was that now I've got a way to backtrack and find the side length of the large building. Because if you think about it, what we did here was we did 9 times 9, which gave us 81. 12 times 12 gave us 144. And so here, if I know this square is 225, I just have to reverse that process. Is what times what would give me 225? Or another way to say it, like we've been discussing in class, is what is the square root of 225? Well, that turns out to be 15. So by knowing the area of the large building, we could backtrack to find the side length of the large building, which was 15 by 15. So that's one key idea that I'm hoping you walked away with, that by knowing the areas, you could find the side lengths. Alright, now let's take a look at another discussion we had. Now, this part, don't copy down in your notes. This is just a sample of the table that we did in class. And the idea here was that we were supposed to be looking for some patterns. And you guys came up with one in particular that really helped us out, which was this. That if we looked at the area of the small square for any given proposed blueprint and the area of the medium square, that if you added those two together, it turns out they were always equal to the area of the large square. 16 plus 49 does equal 65. So I'd take a look at this one. 9 plus 25 did equal 34. And it held true for all these. 36 plus 64 does turn out to be 100. And so what that gave us is another key idea, which was that instead of doing this the hard way, which was to dissect the square, rearrange the pieces, tape it all back together, and then count the squares, that we have a much faster way of doing this. That we can take the area of the small building plus the area of the medium building, and that always equals the area of the large building. And this was a much faster way to find this area rather than dissecting it and taping it back together again. So that was the second key idea. So now, if we take those two ideas and put it all together, here's what we get. I've got another blueprint here, but this time instead of putting in measurements, I'm just going to use the generic measurement A. And I'm going to make this the generic measurement B. So if you think about our process, what we would do is we would add on our squares. There's the building on side A, which has a side length of A, and of course the medium building. And in our generic blueprint here, has a side length of B. Now, just like before, we're going to skip over this one because we don't know this one. We're going to call it C in just a sec, but for now let's just do it just like all the others we've done in class. So, now let's find the area of the small building. Now, even though we don't know what A is, we know it's an A by A building, and A times A, length times width, is A squared. So the area of the small building is A squared. Same thing for the medium building. Since it is a square, this is B, the area of the building is B squared. Alright, which gets us to our two key ideas. That if I add on the last building, that instead of dissecting this and cutting it and retaping it, we now have found out the pattern that if I take the two smaller areas, I can add them up and I get the area of the third square. So a way I could write this is A squared, this one, plus B squared. And so a way to write this is A squared plus B squared. Now, I'm going to do this last part a little out of order. Let's assume if this is A and this is B, we're going to call this side C. So another way to find the area of the large building would have been to say, well, if it's a C by C building, then its area could also have been written as C squared. So if this is C, I can call the area of the large building C squared. So we actually have two ways to find the area of the large building. And so it turns out that this is the Pythagorean theorem. That if I take the area of the small square, A squared, plus the area of the other square, the other of the two smaller squares, B squared, that if I add them together, I always get the area of the large square, C squared. And this is what's called the Pythagorean theorem. This holds true for any right triangle. Now, it doesn't work for all triangles, but any right triangle, that 90-degree corner, that the two smaller squares will always equal the large square.